Hello everyone, and welcome. Today, we're going to explore a major leap forward in AI, training native GUI agents to reason and act. The current paradigm envisions native, single vision language model, VLM, agents that can handle complex, multi-step navigation across both web and mobile environments. Our edge here is that we are achieving proprietary-level performance, but doing so exclusively with open-source models and a highly efficient post-training pipeline. The result of this work is what we call the GUI-Libra framework, alongside our new GUI-Libra 81K dataset. Let's look at the current landscape. There's what we call a long-horizon capability gap. Currently, open-source native agents are fantastic at executing single atomic actions with great visual grounding and high precision. However, they really struggle and fail when it comes to multi-step, reasoning-heavy navigation tasks. On the other hand, proprietary systems like GPT-4o have strong high-level planning capabilities, but they are closed-source, expensive, and rely on brittle, multi-module setups. Why does this gap exist? It's because current open-source ecosystems lack action-aligned reasoning data and use generic training pipelines that just don't understand the unique physics of GUI environments. We've identified two hidden bottlenecks that cause this. The first happens during supervised fine-tuning, or SFT. We call it reasoning grounding interference. Standard SFT forces a trade-off, generating long, descriptive chain-of-thought reasoning actually degrades the model's visual grounding accuracy. The second bottleneck occurs during reinforcement learning, or RL, and we call it reward ambiguity. Stepwise RL suffers from partial verifiability. In a GUI, multiple actions might be correct, but our offline data only verifies one specific path. So, if the model takes a valid alternative action, it goes uncredited and gets wrongly penalized. To shatter these bottlenecks, we built the GUI-Libra framework. It's a tailored training recipe that avoids massive, expensive online RL. By curating high-quality data and re-engineering the post-training objectives, GUI-Libra aligns deep reasoning with precise acting inside a single native VLM. The framework combines our high-quality reasoning data with action-aware SFT to solve the interference, and conservative RL to solve the partial verifiability. Together, this leads to robust online execution. Let's break down the data foundation, the GUI-Libra 81K dataset. Instead of spending a fortune collecting new live environment data, we retrofitted 170,000 existing open-source trajectory steps. We injected structured reasoning, like observation, reflection, and planning, into this data, and aggressively filtered out the noise. The end result is a highly refined dataset of 81,000 verified steps featuring perfect action reasoning alignment and highly precise bounding box grounding. Now, going back to that first bottleneck, the SFT dilemma. We actually have empirical proof that thinking hurts acting. When we evaluate GUI agents on grounding benchmarks, a clear negative correlation emerges. As the length of the reasoning response increases, grounding correctness drops significantly. Standard chain-of-thought tokens dominate the training loss, which causes the model to prioritize high-level semantic logic while neglecting precise spatial execution. Our solution is Pillar 1, Action-aware SFT, or ASFT. GUI-Libra rescues grounding accuracy without deleting the model's reasoning capabilities using a two-part strategy. First, mixed supervision. We train on a mix of reasoning then action data and direct action data to reduce reliance on overly verbose thoughts. Second, token-level reweighting. We explicitly force the model to care about execution by giving grounding and action tokens significantly higher weights in the loss function compared to standard reasoning tokens. Next, let's look closer at the second bottleneck, the RL dilemma. Standard reinforcement learning works great for math, where an answer is either absolutely right or wrong. But GUI navigation is fundamentally different. From any given state, multiple actions can successfully advance the task, like clicking a magnifying glass icon versus pressing enter on a keyboard. Because offline datasets only verify one demonstrated path, those valid alternative actions receive a zero reward. This conflates genuine errors with creative problem solving, creating biased and destabilizing gradients during training. To fix this, we introduce Pillar 2A, conservative RL via KL regularization. In standard RL, dropping KL regularization often helps, but GUI agents require a KL trust region. Because multi-step errors compound, we use a KL penalty to constrain policy drift. This strictly limits how much the model can deviate from demonstrated actions, preventing it from wandering into unknown state spaces. This ensures that our offline metrics reliably predict actual online success. We also have Pillar 2B to handle those ambiguous zero-reward actions, Success Adaptive Negative Gradient Scaling, or SNGS. SNGS conservatively downweights the gradients induced by ambiguous negative outcomes. Simply put, if the model has low overall confidence in the demonstrated action, the penalty is attenuated to prevent us from over-penalizing a potentially valid alternative. But if confidence is high, the negative update is preserved. To scale this, we use automated offline reward verification. GUI-Libra optimizes against a rule-based reward signal computed entirely offline, eliminating the need for expensive live environment interactions. The reward is a strict weighted sum. 10% comes from a format verifier that checks for valid JSON tags, and 90% comes from an accuracy verifier. The accuracy verifier requires perfect alignment on action type, a value match, and a precise grounding match within the target bounding box. So, does it work? The results speak for themselves. On rigorous offline benchmarks, GUI-Libra dominates. On Android Control v2, the GUI-Libra 4B model saw a 13-point increase, and the 8B model saw a 9.5-point increase over their base models. On MMind 2 Web v2, our 3B model hit 42.7% accuracy, effortlessly outperforming larger open-source models and even beating GPT-4o wrapped in external frameworks. But offline metrics are just proxies. Live environments are the ultimate test. On platforms like Android World, GUI-Libra models shatter their baselines. Our GUI-Libra 4B model achieved a massive 15.6% jump in task completion on Android World. It matches GPT-4o and beats heavily trained multi-module frameworks, all while using just a single, natively trained VLM. To understand why this works, ablation studies confirm our architecture's efficacy. First, interference is mitigated. By combining ASFT with RL, we completely erase the reasoning grounding penalty. The model retains over 88% grounding accuracy even when producing long, 200+ token reasoning traces. Second, predictability is locked. By applying moderate KL regularization, we created a statistically robust correlation of 0.89 between offline step matching and online task completion, successfully preventing reward hacking. In conclusion, the future of GUI agents is data-efficient post-training. We've proven that massive, expensive online reinforcement learning is no longer a prerequisite for state-of-the-art navigation. Remember these 3 takeaways: better data beats bigger data, architecture matters, especially using action-aware SFT, and conservative is robust, meaning constrained RL unlocks true multi-step reasoning. Best of all, GUI-Libra is fully open source. We invite you to build the next generation of native agents today. Thank you.